Home, you are here. I'm glad you came today. Thank you. Where were you last time? We didn't see you. I was late. Dad, Home is always late. He's always late. It's a problem. I know. It's okay, Snow. Home is late, but we all have issues. I don't have any issues. Whatever, Snow. What were you doing? I found butterfly. Oh, you were watching a butterfly down by the pond? Yes. And that's why you were late? It was beautiful. Well, okay, I'm glad you're here today, man. So, in any case, today we're going to talk about some solving of equations and looking at the geometric solution to those solving in equations. Great. And see you soon. And that's what we are going to do today. We've got a couple of goals. I'd like to talk about solutions of triangular system. And echelon systems. Kind of show you how to do it. And then secondly, we'd like to interpret geometrically. So I'd like to be able to interpret your solutions geometrically. Let's change this a little bit. So these are what we have in mind to do today. So let's get to it. And I think the way I will do it is by example. So I'm going to give you some examples, and then you will hopefully see how it works. So let's take this. This is a triangular system. X1 plus X2 plus X3 is 3. 2X2 minus X3 is 1. And X3 is 1. So this is a typical triangular system. You have 3 total variables, and there will be 3 lines of equations, 3 equations. And the first equation will contain all 3 variables, the second equation will contain only 2 of them, and the third equation contains only one of those 2. So this is why it's called triangular, is because you lose a variable at each stage. And so, first of all, this comes from a system that isn't triangular, and there's kind of a reduction process. I'm not going to talk about that reduction process today, but it's easy. And many of you already know this reduction process. It's just arithmetic. So this system of equations is vastly not triangular, reduces nicely to a triangular system. And so these triangular systems are easy to solve. So let's solve this one. How do you solve it? Well, we already know X3. X3 is 1. Subbing this 1 into the second equation leaves only X2 as a variable. So you get 2X2 equals 2. So X2 is 1. Subbing that into there. And once you know X2 and X3, you can sub both of those in here. So X1 plus 1 plus 1 is 3. So X1 is also 1. And in a similar way, every triangular system can be solved uniquely for its variables. And that's a key fact about triangular systems. Any questions about that? Oh, probably not. So every triangular system as one and only one solution. And secondly, every system that has a unique solution and one and only one, mathematically the term is unique. Every system that has a unique or only one solution reduces to a triangular system. So if there's a unique solution, it'll reduce to a triangular system, and this is how to find the solution. And every triangular solution also has only one solution. So this is pretty straightforward. I'll give you some problems discussing this kind of thing on Monday. But I'd like to talk about the systems that aren't reducible to triangular systems. Those, in a way, are more interesting. And these are called echelon systems. And again, I think it's probably easiest to give you an example of an echelon system. So here is an echelon system. We'll begin again with three variables. 3x1 plus x2 minus x3 is minus 1. And x2 is 8. So this is not triangular. We have three variables, but we only have two equations here. And we drop down, but we drop two variables here from having three to just one. Not triangular, but this is considered an echelon system. Echelon in the sense that you decrease the number of variables at each stage. So echelon system. Now, I have a system that reduces to this, and let me give this up. So here is a system of equations. So the first equation is exactly the same. The second equation and the third equation is this. This system reduces to this echelon system. And this is the system from problem 5. Of the worksheet from last Friday. And many of you reduced, as I watched the groups, you reduced this system in some way to get something like this. And that was an excellent first choice. Noting that this system was not unique, or how to describe this system, or why this described a line, this was a problem for you, and this is the problem we'd like to deal with today. What is this solution? What does it look like geometrically? So I'd like to talk a little bit now about the geometry here that we can get from this kind of echelon system. Before I do, I'd like to say a couple of things about echelon systems. Every system reduces to an echelon system. This is good news, because if we can solve echelon systems, we'll be able, and we can reduce, we can do the whole thing. And secondly, if, or let's put it this way, a system has a unique solution when and only when the echelon system that you get is triangular. So when we reduce, we'll reduce to an echelon system. If that system's triangular, the solution's unique. If it's not triangular, the solution is not unique. In fact, you'll have infinitely many solutions, and that's what I want to talk about lastly in this video. Let's see, where will I go? So I think I'll rewrite this and erase everything and start to talk about the geometry of these solutions that we're getting. So in the first case of example 1, the solution was x1 is 1, x2 is 1, and x3 is 1. So writing this as an individual location, the solution can also be written as the location 1, 1, 1, which is a point in three-dimensional space. And in example 1, we began with 3 individual planes in three-dimensional space. We looked for solving that system, which means to find the intersection. Geometrically, it means to find the intersection of those planes. Those planes intersect in exactly that one point, which you kind of would expect from 3 planes in 3 space. So this is the geometry of the very first example that we did. We have 3 planes in three-dimensional space. The first 2 planes intersected in a line, and the third plane intersected that line in a particular point, and that point is 1, 1, 1. 1 out on the x1 and 1 up. So there is the solution, that point right there. Triangular systems, unique solution, geometrically a point in the appropriate space, in this case, three-dimensional space. So let's look at case 2, where the solution was a little more complicated. So our echelon system was 3x1 plus x2 minus x3 is minus 1, and x2 is 8, and that's it. This is the whole echelon system. So you might say, well, what about x3? Since there is no information about x3, x3 is free to be what x3 wants to be. x3 is a free variable here. It is what allows you to have more than one solution because it can be more than one thing. It can be any real number. And there's one slightly subtle but not overly subtle point here, is that x3 as a variable has some history. It means something just by the very nature of its notation. x3 represents height in a Cartesian system. But x3 being a free variable here does not indicate height. It just indicates that this can be anything that it wants to be as a variable. So in order not to confuse x3's history as meaning this with the fact that in this context it can be anything, a new letter is used. Usually this is called a parametric variable, usually s or t, something other than these subscripted Cartesian variables that mean something geometrically. So this is a step that you need to do, is when you have a free variable, relabel it with a parameter. x2 is 8, no parameter, x2 is just 8. And then x1 is this. So I'm going to sub in what I know about x2 and now x3's designation as free into this equation. So we get 3x1 plus 8 minus s equals minus 1. And so 3x1 is s plus 9. Oh, x minus 9. And so x1 itself is s divided by 3 minus 3. So our solution now is x1 is s over 3 minus 3, x2 is 8, and x3 is s. So this is our solution in terms of x1, x2, x3. This is an arithmetic or an algebraic solution, but we're interested in the geometry. So I'm going to change this in order to write x1, x2, x3, these mean coordinate variables. So I'm going to create the solution as an ordered triple, which would be part of three-dimensional space. And x1 is s over 3 minus 3. x2 is 8, and x3 is just s. And this is in three-dimensional space, and s is free. Now, I said s is free, but s is really not free. It cannot be a banana. It cannot be an elephant. It cannot be whatever. S is free to be any real number that it wants. So free variable means S is any real number that it wants. So S is anything, as long as it's a real number. And then the solution, any point that satisfies this equation with any S is a solution. So you can take any real number like pi over 17, plug it in there, gives you a solution. So these are all the solutions. And one more thing, I'd like us to know the geometry of these solutions. I'd like you to be able to look at this solution and say, aha, this is a line in three-dimensional space. Why is it a line in three-dimensional space? And what is that line? So let's just check that out. It's not hard to see. So we'll take this solution and I'm going to split it into two parts. A constant part, the minus 3, the 8, and there is no constant added on here, plus a part that involves the variable s. So we have s over 3, no s's in the second coordinate, and an s in the third coordinate. And again, s can be any real number. And now I'm going to factor an s out of this part. So I'm going to get 3 minus 3, 8, 0, plus s times 1/3, 0, 1. S is free to be any real number. And that form right there will show you exactly what the solution is geometrically. This is called the point direction form. This is the point, and this is the direction. This is a lot like the point slope form of lines in 2 dimensions. But let's see where this thing is and what the line is. coordinate axes. This is not S. This is the coordinate axes for all of three-dimensional space. S shows up in this solution. The first thing we'll do is we'll graph the point, minus 3, 8, 0. So minus 3, 1, 2, 3, 8, 1, 2, 3, 4, 5, 6, 7, 8, and then 0. So it's in that plane. So here is the point, minus 3, 8, 0. And now from that point, I'm going to look in this direction, 1/3, 0, 1. From this point, look in this direction. So 1/3 in the x1 direction, 0, so I don't look sideways at all, but I look 1 up. So from this point, I go 1/3, 0, 1. So I look in that direction. And so this is the direction, starting from a point on the solution. Where are all the solutions? If you're at this point and you look any way out in that direction or even backwards in that direction, like a laser beam, these are the solutions. Any point that's golden is a solution, and any solution is golden. So there are infinitely many solutions. There are, in fact, a line of solutions. That line goes through that point, and that line has this direction. So here is an interpretation of a line of solutions, infinitely many solutions, coming from that echelon form for this one example. And this should get you going for the worksheet and the problems worksheet on Monday, and then I'll give you homework on these problems afterwards. I hope you have a great rest of the weekend, and hope to see you soon. Bye. Bye now. Where's home? Left. He's gone already. Okay.